Right. So good afternoon, everyone. Yeah, so I've made an announcement yesterday night on your midterms, which is actually a heavy weightage assessment comprised of 2 hours, a 2-hour paper, okay? So that will be conducted after your term break, which is on Tuesday, 21st of October, right? So that will be in week 8, the Tuesday of week 8. Okay, so this is week 5. Next week is week 6. Then week 7 you have your term break. Then week 8 you have your midterms. Okay, so I understand that you guys have 2 papers next week, is it? Right? Yeah, so I got the request to move the Wednesday extra online class to maybe week 7. Because next week, Wednesday, if I conduct the online class, then I think nobody is going to come because you have a Wednesday 6 p.m. paper, I heard. Yeah, so I think maybe I'll make an announcement on the extra class. I move to week 7, okay? Yeah, I mean, it's still online, don't have to come to school. Yeah, so to facilitate your revision for the midterms, so there's a past year, which is just last year, midterms paper being uploaded already. Okay, so I just uploaded the questions only, right? So you are expected to try out the questions before referring to the answer, which will be uploaded in week 7. Okay, so you can see the questions here, right? So the format will be almost exactly the same, which is comprised of a first part on MCQs, right? So you can see 15 marks MCQs. Then after that, got 2 structured questions. Okay, so structured questions are like 2A, 2B, 2C, that kind of thing, right? So you can see question 2 is a structured question. Then question 3 is also another structured question. Can okay? So usually my midterms got bonus marks 1. So you can see the total is only 70 marks, right? There's no need to force it to 100, okay? I think 70 marks is good enough. But can change one, right? Every year, as I said, right, I see the marks allocated for each question. I roughly balance them, and then I get this total marks. Then you can see that there's another 7 bonus marks. So that means actually this paper, total number of marks is 77, okay? 77. Right, but I take it as it's upon 70. So that implies that if you score 70 and above, you get full marks. 70 and above, 70, 71, 72, all the way to 77, right? You are getting 70 marks. So that means full marks. Okay? You understand, Right? So there's a bonus mark there because there's 77 marks for you to score, but yet it's only upon 70. So actually you have more opportunity to score more marks. You understand? Okay? It's not like I give you the 7 marks for free, right? It's not for free. You still have to try and score, but you got more probability of scoring higher. Okay? It's not like I give you, 7 marks free, give you. Not like that. Okay? You have to make your effort. So therefore, that'll be for the midterm test. Okay? The past year paper, right? So this year will be about the same, but you might have noticed that for this midterm test, because last year we have an open book examination, right? Open book assessment, which the students are allowed to use their laptop. Okay, so they are also tested on the computing or computational questions. For example, let me just show you like this one. So this one perform linear regression, okay, using Desmos. Right, so certainly this year you will not be able to do that because it has been converted to a closed book assessment already. So everything become closed book with formula sheets. Okay, so then of course you can still do, right? Because first one maybe you can't do, but from part B onwards you'll be able to do. So still tested on the mathematical concepts. Can okay? Yeah, so that will be for the midterm test. So topics 1 to 4. Yes. Okay, good question. Okay. Yeah, of course there will be error carry forward. Error carry forward. So which means that if let's say this is your A and B, I don't care what's your A and B actually, right? So you get some value lah. Let's say if you got the wrong value, it's okay. Then part B, you just use the value that you got in part A. Okay, then if you like, let's say for example, you are supposed to get a velocity function, you're supposed to evaluate the acceleration function, which means just differentiating this thing. Okay, so if you differentiate with the wrong A and B, but your differentiation is completely correct, and you can also answer this question by substitution of t equals to 4 seconds to calculate the acceleration, then you get full marks. Anyway, you get full marks. Okay, so if you get the A and B wrong here, but this one is testing you on the acceleration function, nothing to do with the A and B here, they are just constants. So therefore you sub in, right? Everything else is correct, okay, following your wrong A and B. Then this, you'll get full marks. Fair, right? Okay? Yeah, but of course this is in this context, right? But in another context is that, let's say for example, the function you hear, the function you get here, let's say you're supposed to get, let's say the velocity function for example, okay? But the velocity function you get here, let's say wrong. Then you're supposed to get the acceleration function in part B, let's say. Then like that, right, you will not get full marks based on the wrong velocity function here. Because when your velocity function is wrong, it is possible that your acceleration function is easier to obtain. You get my point, right? So therefore, your acceleration function, which is based on the wrong velocity function, will be deducted marks, even though if you did all the differentiation correctly. Because you might not have maybe a more difficult term to differentiate. You will still get some marks. Okay, you will not like get like 0 totally. Can So there will be some degree of error carry forward. Okay, if it's just involving constants, then the error carry forward will be complete. Okay, in any case, okay, for midterms, because it's not under the school, I mean, it's not directly so-called conducted by the exam unit, right? So what happens is that after the midterms, you will be able to assess your marked script online in Gradescope. Okay, so then you can see like which part you got deducted marks and what is the reason for the deduction. If you like find that the deduction is unfair, or you feel that this is probably having some error, you can come and discuss with me. Okay, if I find your reason fair, right, then I will like award you higher marks. Okay, yeah. So now we are going to talk about Tutorial 3. So for the earlier class, I managed to finish the whole tutorial. So we'll be doing the same for this class. Okay, certainly I didn't manage to finish all questions. I don't want to as well. You can request for further questions for me to go through. Okay, for those questions that I did not go through. So for question 1, actually we have already dealt with this limit already when we covered L'Hopital's rule yesterday. So this guy is actually your f prime a, okay? Because if you look at the L'Hopital's rule derivation on topic 3 yesterday, okay? So I'm addressing this part here, right? This limit as x approaches a, right? And you have your f of x minus f of a divided by x minus a. This fraction is the slope of the secant line, okay? So you can see that this is really just change in f, the numerator, over change in x, the denominator. So it's this slope, okay, of this light blue secant line here. So therefore, if you take limit as x approaches a, then the light blue line is going to approach the tangent pink line, okay? So therefore, this tangent pink line is at a. The tangent pink line, right, is a tangent at point A. So therefore, it must be f prime a. Okay, the slope, right, of the tangent pink line must be f prime a. Okay, so therefore, this is something that we have gone through already. Any questions on the concept? So interestingly, this thing can be converted to the standard limit definition for the derivative. Okay, because the limit definition, right, the standard limit definition is limit as h go to 0, then you have f of x plus h minus f of x divided by h. Okay, so this guy is my f prime x. So this is similar to this. Okay, this form is actually similar to this form. Right, if you didn't observe, you can just let h be x minus a. So for example, right, now here, if you let x be, let h be equivalent to x minus a, so that means x must be equivalent to a plus h. Agree, right? Okay, so if you do this, then you are going to get this limit being rewritten as f of x, right? But x is a plus h, ma. A plus h minus f of a. Then divide by, so x minus a is really h. Okay? So as x approaches a, h approaches 0. Okay? So therefore, if you do this substitution, you are going to get this form of the limit. But this form of the limit, right, you can see that this guy is similar to this guy, right? It's very similar. It's just that the x become a. You see? The x here become a. Then the x here become a. So therefore, this thing, right, is actually f prime a. Okay? So the x here, and the x here, you just change to the a, and a. Is that right? Similar. Okay? So this is another way to kind of deduce that this limit expression is f prime a. It's just the slope of the tangent at point A. Any questions? So let's look at question 2, which is deriving from first principles using the limit operation, the derivative of each of the 5 functions shown. Okay, I didn't do any because the earlier class didn't request any. So do I need to go through any one of these? Very good. Oh, okay. Very good. Then question 3, I got the request earlier to go through B, D, and E. Okay, so I just quickly jump through them as well. So you can see for question 3E, I think the main difficulty is in the derivative of the exponential function with a non-exponential base, non-natural base. Okay, so if you look at your table of derivatives, which is the blue table that I highlighted here, this guy. Okay, so you can see that if you differentiate a to the x, you must get a to the x ln a, right? So therefore, we're going to make use of that. Okay, differentiation of a to the x equals to a to the x ln a. But when we differentiate this fractional expression, we have to use the quotient rule. So you can see that there's a lot of echo. Hold on, I think I cannot use this one. Test, sound good. So you can observe that when you use quotient rule, right, you have to hold the denominator first. Then after that, when you differentiate this 2 to the pi x, 2 to the exponent of pi x, you have to use this blue part already. Okay? So, but there's a nuance here. And that is, right, this exponent is x, then you can write like that. But this exponent here, right, is not x, it's pi x. So which means that you have to apply chain rule, because the pi x is like a function of x, let's say g of x. So therefore, when you differentiate this, you can see you have to put down the a to that something, right? A to the g of x. Because the first term, you are actually differentiating the exponential function with respect to the exponent. So it's actually d dg. okay, differentiating a to the power of g with respect to g. So then you put down the ln a, but this is not all. Because this part you only differentiated respect to g, you are supposed to differentiate respect to x. So hence you have to multiply by dg dx. So actually we applied the chain rule here. And now your g of x is just pi x. So therefore you can see I put down 2 to the pi x, which is this term, followed by ln 2, because a is 2. Then followed by g prime x. But g is pi x. So differentiate pi x with respect to pi. Differentiate pi x with respect to x. So you get pi. So then the rest of the terms are pretty standard. So you hold the 2 to the pi x and you differentiate this cube term. So you bring down the 3 and then the x squared plus 1, you have a square. And then next you have to have chain rule. Differentiate x squared plus 1, you get 2x. Then divide by the square of the denominator, you get a power 6 there. Okay? Then the rest are actually just trying to factorize and simplify. Okay? Because from here you can see that we have a common term that is 2 to the pi x. This and this. So might as well factorize it out. Okay? After we factorize already, then we are left with the remaining terms in the bracket. Then I also realized that actually there's a x squared plus 1 square. There's a common term as well. So I factorize out again. Okay? After factorizing out, then I realized that, oh, this is power 6, this is power square. So therefore I can divide away. So hence this denominator becomes power 4. Okay? So that gives the final answer. Alright. Can 3e. So then 3b and 3d. So for 3d, 3b first. So this one basically just use product rule because you can see that 3b, right, you have function of t times another function of t. So you use your product rule. And then when you differentiate ln of this guy, right, it must be 1 over the whole argument in the ln. Then after that you use chain rule. So you have differentiating t squared minus t giving you 2t minus 1. Then there's another term of the product rule that you can get easily, just 3t squared, then put back the ln. And then this guy, use chain rule, you get pi secant square pi t. Then you simplify, you get the answer given here. Okay, looks easy for you guys. So then 3d, the thing here is that you have two functions multiplied to each other. So this one is 7 to the power of y, and this one is log base 7. Okay, so maybe just to simplify the process, I bring down the 1/3 due to the log. Okay, but if I bring down 1/3, I can actually factorize it out of the whole expression. So I have an easier expression to differentiate. Then the 1/3, when I differentiate, I can just put outside. Then 7 to the y, so you just now we addressed already. So you just put back 7 to the y, but you must always ln the base. So ln 7. Then you hold this guy. Because this is a product, so you have to use product rule. Plus 7 to the y. And now when you differentiate log base 7y, right, you have 1 over y, then times ln a, which is ln 7. So this guy is using the table once again for the logarithmic function, which is this one. Differentiate log base log base ax, you're going to get 1 over x, but you have to put a ln a at the denominator. So which is what is being done here. Okay, then the rest just simplification. So therefore I get this form. May not be the same form as the given answer, but this is as simple as it gets. You can factorize out the 1 over ln 7 if you want. So I think differentiation using all the various rules whenever needed. Hopefully it is okay for you guys. Any questions? Since I have gone through 3 parts of question 3, the other 3 parts I'll leave you to DIY. So next we look at question 4. Yeah, so question 4 I went through part B, which is using implicit differentiation to get the derivatives of all the inverse trigo functions. So this one actually similar to what is being done in the lecture Because in the lecture we did for sine inverse and tangent inverse. Okay, so this one is cosecant inverse, right? But basically the trick is the same lah. So you just let y be the cosecant inverse x, then you invert the function. So you get x equals to cosecant y, right? And then cosecant is 1 over sine, so it's 1 over sine y. So from here you have to use implicit differentiation. So you d dx the whole thing. So when you differentiate x with respect to x, you get 1. Differentiate 1 over y with respect to x. So therefore, you can see that this is sine y to the power of minus 1. So therefore, bring down the minus 1, then the power becomes minus 2. Then, not to forget, you have to use the chain rule because you differentiate 1 over first. Then now you have to differentiate the sine y. So that gives cosine y. But remember, you're doing implicit differentiation. So differentiating with respect to x here, right, will require you to have another chain rule term, the y prime term. Okay? So once you see the y prime, then basically just isolate that because you want this derivative. So isolate it, you get minus sine square over cosine y. Okay, nothing much, I just bring across. And then I noticed that, oh, this one you have to evaluate further because it's in y, but you want in x. So therefore, you have to look at this expression here. So you see that this is actually sine y equals to 1 over x. So that means that you have to draw a triangle trying to get the x and y put in their correct places. Now you sine y, right? So you have to sine the angle y. But this is, sine must be opposite over hypotenuse. So the opposite is 1, hypotenuse must be x, so that you can get 1 over x. So that means that the adjacent must be the root of x squared minus 1, because that's from Pythagoras. Then you see here you got cosine y. So therefore you can write down cosine y as adjacent over hypotenuse, right there. So therefore that enables you to replace all the sine and cosine terms already. So hence you are getting 1 over x squared, which is your sine, right? Because you have sine square here, and then your cosine. So because you are inverting cosine, so I just swap the terms, swap the numerator and denominator, then you simplify, you get the answer. So the same approach can be applied to all other inverse trigo functions. Do I need to go through any other one? No request? Y be cotangent inverse x. So, you are trying to get y prime. Simple as that, huh? Okay, because you want to differentiate. So then you need to invert. Okay, so when you invert, right, you are getting x equals to cotangent y. So then because you want to get y prime, right, so you got to differentiate with respect to x. Okay, so now you do a d dx, which is differentiating implicitly. So differentiate x respect to x, you get 1. So now differentiate cotangent y with respect to x. So I don't know what's the derivative for cotangent. I didn't remember that. Okay, but I can always put it into 1 over tangent. I mean, if you refer to your table of derivatives, you can just write down the derivative for cotangent y as well. Okay, but I can always write it as 1 over tangent y. So you see what happens here is that I can easily use the chain rule. So therefore I have minus 1 over tangent square y. Because tangent y minus 1, my power minus 1. I bring down minus 1, then the power becomes minus 2. But then I need to use chain rule. Right? I must differentiate the tangent y also. So it becomes secant square. But because I'm differentiating with respect to x, not y, so therefore I need to have chain rule again, y prime. Okay? So of course that expression, you can simplify a lot. So this is tangent square, right? So 1 over tangent square is cotangent square. So therefore it's really just cosine over sine. So minus cosine square y divided by sine square y times 1 over, secant square is just cosine square, 1 over cosine square, and times y prime. Oh, forgot my prime. So then you observe that actually the cosine square and the cosine square can divide away. So this one divide away. So then you simplify to y prime. So you get y prime equals to, so you can see the 1 here, right? So it has to be, looks like you're just going to get minus sine square y. Is that right? Okay, so you have found that the derivative can be expressed in terms of y, but what you want is x. So you got to draw the triangle. So this part, right, is tangent y equals to 1 over x. So tangent y equals to 1 over x means y is an angle in a right angle triangle. Then 1 over x, right, must be opposite over adjacent, because that's what tangent means, right? Opposite over adjacent. So that means it has to be 1 as the opposite, x as the adjacent. Okay, and you need sine square. So which means that you need the hypotenuse. So therefore the hypotenuse is going to be the root of x squared plus 1. X squared plus 1 square lah. So once you have populated the three sides of the triangle, you can observe that your sine y, right, must be equivalent to opposite over hypotenuse. So 1 over root x squared plus 1. Okay? So then with that, right, you can actually write down your answer, y prime in terms of x already. So this is really minus, right? So you square. So therefore you square away the square root. Good. So you can apply the same approach to the other two inverse trigo functions. So then of course your table will be more complete. Okay. So let's look at question 5. So in question 5, okay, this one I want to go through. Why? Because you might have a confusion with this, in the sense that in this case, I purposely go and write that x is an implicit function of y, not y as an implicit function of x. Because you are probably used to dealing with y is an implicit function of x. Okay, but it can be the other way around, right? So now x is the function, y is the variable. So it can be x of y. Now I'm supposed to determine dx dy, not dy dx. Okay? So therefore, I now have to dy the whole thing. So when I dy, right, because x is an implicit function of y, so I have to use the chain rule when I'm differentiating a function of x. So it's like opposite of what you have done in differentiating implicitly y as a function of x. Okay, this one is x as a function of y. So you see, so x squared is a function of y. Y is another function of y. So this one you need product rule. Okay, you need product rule. So when you dy, right, you can see that I hold x squared first. I differentiate respect to y. So dy is just 1. Right? They're differentiating y respect to y. That will give you 1. Don't put y prime. Don't put y prime. Okay? Because y is the independent variable now. Right? So then after that, you have to hold that y, differentiate x squared. But when you differentiate x squared, you must understand that this x squared is a function of y. So which means you have to use the chain rule, which is your implicit differentiation. Okay? So hence you have what? 2x first. Now you got to put x prime. Because dx dy is x prime, what? Okay? So which is what happened here. So hence I get 2x times x prime in the second term of the product rule. Same thing goes with ln x. Now x is the function. So when I differentiate, I must differentiate the ln x respect to x first. So I get 1 over x. But I'm differentiating respect to y, not x. So I have to have a x prime. So the chain rule applies. Okay? So that gives the third term here. And then differentiate sine y, you just get cosine y. Remember, y is now the variable, the independent variable. Then the rest are pretty much isolating the x prime term, right? And throwing the rest of the terms on the right-hand side. Then after that, just divide across. You get the answer for x prime. Then you have to apply implicit differentiation, okay, to get dp dz. That means I just like anyhow choose the alphabet, right? I don't want like y as a function of x, okay, or x as a function of y. I'll just give you some other alphabet. So by right, if you understand the concept, right, you'll be able to apply the implicit differentiation regardless of what alphabet you get. Okay? So which means that you cannot memorize. Okay? You have to understand when to put in that something prime term. Question? Okay? Question 5 done. So let's look at question 6. The equation of the tangent and normal. The earlier class didn't request any. Do I need to go through any one of them? So basically just find y prime, right, implicitly. Okay, so look at the functions there, right? You have to find y prime implicitly because you cannot isolate y prime. I mean, you cannot isolate y as a function of x. So then after that, you just get the gradient of the tangent and the normal by substituting in those points, 2, 0, and 0, 1 given. Then your normal line gradient is just minus 1 over the gradient of the tangent line. You just sub into your straight line equation. Do I need to do? No need? No need? Good. Okay. Question 7. I got a request to go through 7b earlier. Okay. So I think the y prime is easier. The y prime is a bit more problematic, but actually not that much. Okay. Hold on. So let me just capture this and maybe compare the answer later on. Because I didn't finish the whole simplifying part. Okay, so you just focus on this part first, right? So I'm trying to get dy dx, which is my y prime, right? So my implicit function is x, y, e to the y equals to 1. So of course I use implicit differentiation, right, d dx. So you can see that this one is a function of x times function of x times function of x. Okay? So therefore I need to use the product rule with the 3 terms, take turns to differentiate each term one by one. So then I differentiate x. So I put down y, e, y, the first term. So I hold x and e to the y. Then I differentiate the center y here, the middle y. So therefore I have a y prime. Then next I hold x and y. I differentiate e to the y. So differentiating e to the y will give me e to the y again. Okay, but so become x e to the y multiplied by 1 plus y. Okay, then this right hand side is this term, throw across. So therefore I just divide y prime. I get this division, this divided by this. Then the e to the y and e to the y can cancel off. So therefore I get this minus y over x times 1 plus y. Okay, which is in agreement with the answer. Yeah, so then for y prime prime, you can get it from here, no problem. Okay, this y prime prime, I mean you just differentiate y prime. Then you just apply your usual differentiation, right, to this expression using quotient rule, you can get the answer. Okay, but it's probably going to be a little bit more tedious because quotient rule, we don't like quotient rule. Okay, so one of the maybe workaround is from here. You can differentiate implicitly this part also, what? Because you're going to get the y prime prime term whenever you differentiate the y prime term. So which is what we did. Okay? So we divide by e to the y throughout, so we simplify the whole expression. You see? Right? Just e to the y get eliminated every term, in every term. So now we apply implicit differentiation again to get the higher derivative. So see, differentiate y, get y prime. Now this is function of x times another function of x, because y prime is also a function of x, implicitly. Okay? So therefore, I use my product rule. Okay? So I hold y prime, differentiate x. Then I hold x, differentiate y prime, I get y prime prime. So then the x, y, y prime got 3 terms, 3 functions of x multiplied together. So I have to apply product rule again. You see? So I differentiate x, I get y, y prime. Now I hold x and y, I hold x and y prime. So this guy, when I differentiate, I get another y prime. Then plus again, I hold x and y, differentiate y prime, I get y prime prime. Then obviously I can isolate the y prime prime term, what? You see? Y prime prime gets an x, then this y prime prime, there's an xy. Then the rest of the terms, I just throw onto the right hand side. So then I just divide throughout, I get this. Then I notice that actually there's a y prime term at the numerator. So therefore I factorize out the y prime term, but I'm still having this y prime term here. Is that right? Yeah, so how do you get the answer given here? You notice that this answer given here, right, got no y prime inside, but I have y prime inside here. So what can I do? I just sub this y prime into this y prime prime expression. Yeah, so if you sub this, you can see that you're going to have minus minus, so become plus. So let me write. This will be y. This will be y divided by x 1 plus y. Then this bracket, right, 1 plus y plus x, then times this thing. So this becomes minus here. So minus xy over x 1 plus y. Okay, of course can simplify. Then this is over. Now you factorize out the x. Then you get 1 plus y. Agree, right? Okay, the denominator I factorize out x, so I get 1 plus y here. Can you see, x here also. Okay, then this part, right, because I got x, y prime, but I can divide away that x. So this x can divide away the x at the bottom. So I get just y over 1 plus y. Okay, but I need to make a common denominator so that I get only a single fraction. Can I? Okay, wait, let me see. So hold on, I just want to change the color. Because this part is using the same thing. Okay, so the pink part uses this substitution. So from here you can see that this is equivalent to y over x squared. Y over x squared times 1 plus y squared. Can Okay, I just factorize out this whole thing. That means what is left in the bracket will be a numerator. Okay, so this one is really taken out. So at this part, right, we're just going to have, so this will be 1 plus y square minus y divided by 1 plus y. I just skip one step because, okay, this part take out already. This part take out already. So you look at this part. So I want to make common denominator. The denominator here is 1 plus y, then this is 1 plus y. So I just multiply a 1 plus y to this 1 plus y. Okay, so you can see the first term, 1 plus y whole thing square divided by 1 plus y, I get this 1 plus y. Then minus y over 1 plus y. This term. Is that right? Yeah, then obviously this you are going to get, why I do it? Why I do that? Oh, stupid. I don't even need to do that. Because I can split up the fraction here. I notice that I try to oversimplify. Okay, so let me just go back a little bit. Let me factorize out the x squared only. Okay, this x times this x. So I'm having this 1 plus y squared at the denominator. Then there's a 1 plus y here. Then there's this minus y over 1 plus y. Okay, so basically I can get an answer here. Because y over x squared, you leave it outside. Then you look at this first term. 1 plus y divided by this. So you are going to get 1 over 1 plus y. So that's actually your first term. Because it seems that I'm supposed to get minus y over 1 plus y cubed. Should be this answer. Hold on, let me see if I mess up anywhere. Okay, this one is sub in. Let me see. So minus, I get plus. This one is a plus. X. Yeah, looks legit. Okay, I think I better go back and check. This may be having some error. Either this or this. Okay, so let me check and upload the corrected writings. Okay, but in any case, right, what I'm trying to demonstrate here is that you can apply the implicit differentiation more than once to get your higher derivatives. So certainly I can also differentiate here to get y prime prime. Is that right? Okay, so let me get the correct answer by tomorrow, and then I'll upload the writings, the corrected writings. It didn't say, right, what is this function, okay? But what is important is that there is this base function, that is a function of x squared, which means it's still a function of x, to the power of another function of x. So this will require logarithmic differentiation, which means that you have to ln both sides first, okay? And then you can bring down this root x. So it becomes a product. So then we just apply the product rule. So when you ddx left-hand side, you always get g prime over g, because you have ln g here. Then for this guy, right, I differentiate root x, I get 1 over 2 root x, hold the ln, then hold the root x. Then after I differentiate this. Now when you differentiate this, you have to be careful. Okay, because you are differentiating ln of f of x squared. So you get 1 over f as your first term. 1 over f. Then next, you must use chain rule. So you must differentiate f, okay, with respect to x. So therefore you get, you have to differentiate f with respect to x squared. So that's question 8 and... Okay, question 9, I only went through... by the way, question 8, the rest, do I need to do or not? Logarithmic differentiation. Basically just ln both sides and then use your product rule. Any requests? No need, quite straightforward. Okay, question 9 is once again testing you on the derivatives, but with the values given there, so you're supposed to choose the correct values to sub in. Okay, C is a bit more tricky, just like that question 8 that we have gone through, because of this thing here. So this is like g of 3 of f of x, okay, g of 3 times f of x. So now when you do a r prime, you have to do chain rule, okay? So you see, the first one is your g prime first, okay? Differentiate g with respect to this 3fx. Then you have to multiply. Now, you have to differentiate 3 times f of x with respect to f of x. So it becomes 3, okay? So this is like differentiate 3f with respect to f lah. So therefore you have 3. But you have f of x here, what? So therefore you have to differentiate respect to x for this f. So hence you get f prime x. So you see the chain going on. Okay, so if you simplify, then you just get 3 times of f prime of x times g prime, right, of 3fx. So at x equals to 2, you have to replace all the x by 2. So r prime of 2 will be 3 times f prime of 2. Then multiply by g prime of 3 of f of 2. 3 times f of 2. So the f prime 2 you can find. 3. G prime 3, f of 2 you can find 1. So that means this is what? This is g prime of 3 times 1. So it's g prime 3. Then g prime 3, you look here, minus 4. So therefore the answer is minus 36. Okay? So basically this second part should be correct after if you have done the first part correctly. Okay? Because this 3 here, right? You have to chain rule it. Yeah, it's 3 times the fx value. And then this g is a function of this. Okay? So because 3fx is just another function, so it's g of a function of another function f. So that's why you see the chain rule applied 3 times here. First time, second time, third time. Okay? I mean 3 terms, not apply chain rule 3 times. You have 3 terms. So that's for question 9. I think A and B you should be able to do. Okay? Quite easy. So question 10 is about evaluating if the function is differentiable. Okay, so I did for part B. Right, if you can do part B, then you will be able to apply to part A as well. Then part C is just checking whether the function is differentiable at x equals to 0. Right, because you can see x squared plus 1 and x cubed sine x plus 1 is differentiable in their own intervals. So I only want to go through part B here, because this one, you need to write it into piecewise manner. So every time you see the modular sign, it's an indicator that you have to rewrite in piecewise. Okay, so this is not the first time we have done this, right? But just to reiterate, every time you see modular sign, right, you have to think about 2 possibilities. when the argument 2x plus 1 in this case is positive and negative. Okay, so they will give you two different functions. When 2x plus 1 is positive, the modular sign doesn't do anything. So you just remove it, or you can replace it by a bracket. Okay? And because 2x plus 1 more than 0, more than or equals to 0, implies that x is just more than or equals to half, or sorry, minus half. Okay, you can just bring the 1 across, then divide by 2. Then if 2x plus 1 is less than 0, then the modular sign is going to multiply a minus 1 to it, so that it becomes positive. So 2x plus 1 itself, if it's negative, then you multiply a negative to it, so that it becomes positive. Okay, that's what the modulus is trying to do. So then you see that you have two different functions, one without a minus and the other one with a minus. And then in this case, right, x must be less than minus half. Okay, so we notice that this exponential function and this exponential function, they are continuous and differentiable in their own intervals. Okay, so we only need to check at x equals to minus half, because that's the interval transition. So first of all, we check continuity. Okay, because if it's not continuous, then it is also not differentiable, right? But when we check continuity, we just sub in the limit at x equals to minus half. You can see from here. Okay, so nothing much. You sub in minus half. So if you have minus half minus, which is on the left, then you have to use the red color function, the f2 function. Okay, so you get 1. Then if you sub in minus half plus, which is on the right of minus half, you have to use f1, okay, because that's more than and equals to minus half. So therefore you also get 1. So hence you get continuity at x equals to minus half. So you fulfill the continuity condition, and now you're going to check the differentiability condition. So differentiability must only exist if you have your tangents being collinear. So then you have to get the f prime. So therefore from the original function f, now you have to differentiate. So this first function e to the 2x plus 1, when you differentiate, right, you just chain rule down the 2. So therefore you got 2e to the 2x plus 1. Then same thing goes for the f2 function, because you have a minus 2x here. So therefore you chain rule down the minus 2. So then you just check the limit of the slopes on the left and on the right as x approaches minus half. Okay, so minus half minus, you use this this red color function, then you get minus 2. Okay, then for the minus half plus, so you use the blue function, you get 2. So minus 2 not equals to 2. So therefore, the tangents are not collinear. So if the tangents are not collinear, it means that you have a sharp point at 2. Okay, so if I draw this, right, you'll see that this thing will be at minus half minus on the left is downward sloping. Then for minus half plus is upward sloping. Okay, so therefore in this case, right, it will not be collinear. Okay, so this point at minus half is not differentiable. So this is not smooth. So not smooth means cannot draw tangent, because the tangent on the left and on the right, right, they don't form a straight line. So cannot draw tangent means no slope of the tangent. No slope means not differentiable. Is that right? Okay, so this is checking differentiability. Okay, 11, I didn't do, because it's the same kind of question as the lecture example. Alright, so this one I'll skip. You try out on your own. Okay, then it will be question 12. Okay, question 12, I think there's an error, which I will go and correct later on. Okay, but let's look at the concept delivered by the question. So you have this cloth manufacturer, Mutu, producing boats of fabric with a fixed width. Okay, so one boat of fabric is like one row of cloth. Okay, then from his experience, he models the cost of producing X yards of this fabric to be given by this expression. Okay, so you see at x equals to 0 to 100, right, you have the linear function, which is 2x plus 50 in the green line. Then when you have x more than 100, then the cost function transits to a root x plus b. So a root x plus b, right, is this blue curve here, because it's a root x, right? So it tapers off as you have more x, as you have a bigger x. So now, right, part A, it says that from an economic perspective, explain why possibly the cost function is linear when x is smaller, the green part, and transits to a root function when x is bigger. Okay? So I think this part, we can understand that this is probably due to the economy of scale. Due to the economy of scale. Okay? Because this is the cost of production. Cost of production means you need to, for example, buy the raw material. Okay? Like threads and whatnot. So therefore, as you buy more, right, you get more discounts. You buy more, you get more discounts. So therefore, as your production length increases above 100, right, then you can see this part, the cost actually tapers, right? So therefore, the increment is less, right? It will not flatten, right? It will not be so-called going towards a horizontal line, because it's not possible that as you produce more, you don't incur additional costs. That doesn't make sense, okay? But it's just that it tends to have a smaller and smaller gradient. Okay, so the incremental cost of production, or what we call the marginal cost of production, actually decreases as you produce more and more. Okay, which is why many people try to expand their businesses, right? Because to make money, right, you got to try to manage your costs as well. Okay, so that's also the reason why many F&B operators, as what the news have been reporting these days, right? Many F&B local operators, they cannot survive, okay? Then taken over by big chains, right? I mean, even when the landlord raised the rent, right, the big chains can still operate. Why? Because big chains got economy of scale. When they buy ingredients, they buy for all the restaurants at one go, so they can argue for a very low price as compared to the mom and pop shop, which can only argue for so much, okay? That means they cannot get the discounts that the big players are getting, right? So that's for part A. So then, part B, so this one you DIY because it's the same as what we have gone through in the lecture example. You want to solve for A and B, right? Because your cost model should be continuous and smooth. And this is pretty logical. Because the cost function cannot suddenly jump, right? Okay? Suddenly you go above 100, then your cost function suddenly jump. Doesn't make sense. So Motu knows that, right, the cost model must be continuous at x equals to 100. That's one. Okay? But he also knows that, right, the rate of change of his cost, the additional cost, the marginal cost of production, right, cannot suddenly change the slope as well. Okay? So he feels that, right, at this x equals to 100, you have a smooth transition as well. Okay? So that means he wants this point at x equals to 100 to be continuous and differentiable. So therefore, we just try to satisfy the two conditions of differentiability, solve for A and B, and you are going to get 40 and minus 150. Sorry, this should be minus 150. Yeah, so that's for part B. Then for part C, okay, for part C, you have to be careful because they ask you to calculate this, right? So this, because C at the 101 yard is using the blue function. Because 101 is more than 100, This 101 is more than 100. So you have to use this blue function, okay? The A root x plus B, right? Which is 40 times root 101 minus 150. Your A and B just sub in, okay? Then the 81, C of 81, 81 is inside this interval. So you have to use the first function, okay? Right? So therefore divide by 101 minus 81 is just 20. So you should get approximately $2 per yard. So in my answer I put 2.1. That's incorrect. Okay? You get about 2, I think the exact number is 1.99 something. Right? But in any case, you can approximate that to about $2 per yard. Okay? So you can see that the unit is just cost, which is in dollars, divide by change in yard, which is still yard. Change in length is still length. So therefore, it has to be dollars per yard. So then the main thing is, what is this ratio representing in layman? What is this ratio representing in layman? Okay? So you can see that this is a difference in cost, correct or not? It's the cost at 101 minus the cost at 81 yards. So it's a difference in cost. So that difference represents what? Represents an increase in cost. Okay, this is an increase in cost. So therefore, when you divide by the number of yards here, right, it means to say you are looking at the increase in cost over the number of yards, okay, that you manufacture. So therefore, right, this is what? Increase in cost per yard. So increase in cost per yard is $2 per yard. Okay? So therefore, this ratio, because you are taking two distinct points, 101 and 81. So this represents the average increase in cost per yard. Okay? So is this what? Average increase in cost per yard when producing the 81st yard to the 101st yard. Can Okay? So because as you increase production, right, you need to incur more costs, more raw. Yeah, so that's for part C. Then for part D, it relates to part C. So you're supposed to state the unit of C prime, but C prime is just dC dx, what? Okay, but dC is just change in cost, so still dollars. dx is just change in yard, still yard, right? So it's still dollars per yard. Okay, but what's the so-called difference between dC dx and this finite rate? The thing here is, right, C prime x, okay, is equivalent to 2 if you are looking at the straight line. Because it's 2x plus 50, so you differentiate, you just get 2. So therefore, that is actually C prime 100. 100 is inside this first function, so you have to use this first function. Okay? So you can observe that your C prime 100, right, is $2 per yard. Okay? So this C prime 100 represents what? Represents the increase in cost, or something like instantaneous increase in cost when you are producing the 101st yard, when you are already producing the 100 yard. This 100 means you already produced 100 yards already. Now you're going to go to produce the 101st yard, one more yard lah, right? And that is going to incur $2. Okay? So therefore, C prime is the additional cost when producing the next yard. Is that all right? Yeah, so part E. Now, without calculation, is C prime 100 or C prime 1000 bigger, and why? So certainly, just from the graph, we know that, right, the slope at the green part is 2. But the slope at the blue part, especially far towards the right, will be shallower or smaller than the slope at the green part. Because it tapers, okay? It's still going to approach infinity, but it tapers. So therefore, C prime 100 is going to be bigger than C prime 1000. Okay? And this is, of course, due to the economy of scale, as we have discussed in part A. Okay? You buy more, you get more discounts. Right? So the incremental or marginal cost of production typically reduces. Then they ask, right, do you think this trend is always true? Well, it's true up to the extent when your demand for your raw materials, let's say Muthu, right, the business do very big. So his demand for the raw materials begin to outstrip the supply of the raw materials. Okay? That means the supplier not enough material to supply. So what they are going to do? They are going to increase their prices. Because I can sell everything, right? Which means that my price too low. Okay? Right? So therefore, that will push up the cost of raw materials. So therefore, it is possible that C prime 10 million is more than C prime 1000. Is that right? Okay, so this is something that we can observe lah. Like recently, I think few months back. Is it few months? Okay, maybe close to a year back, right? We are reading the news that the NVIDIA GPUs, the price all shooting up. Because every big company, Google, Meta, additional other companies in other countries, right? All snapping up their GPUs to train their LLMs. Okay, so that's why the price all shoots up. Okay? So demand outstrips supply already. Yeah, so this is for question 12, right? Okay, and that's it. So question 13, I don't want to do, because this question 13 is in the past year paper, right? Anyway, just finding the equation of a tangent at x equals to 0. Okay. So you try first. Anyway, you'll be getting the solutions on the Monday of week 7. Okay, so this one I won't go through, so that you have a chance to try out first. Any questions? We are kind of early today. Any questions? So the rest all okay, Okay, so you try out the other questions first, then there's one question that has probably an error for the y prime prime. I'll double check on that and then upload the corrected writings. Okay, so now I'm just thinking whether I want to continue with topic 4. Wait, let me think. Because most of you are not here. Then I have to ask the other class to watch the recording. You all still can continue or not? Do you mind if I continue with topic 4? Huh? What's that? Question 10. Sure. Yeah. What's that? Question 10. Is it this one? Yeah. You have a clarification to make? Sure. So basically just check whether the tangents are collinear at the transition of the interval, and you have to check for continuity. So the continuity has been satisfied in part 1. So after that, for differentiability, you need the tangents to be collinear. So therefore, you just check the slope before and after minus half. Since you are having two different f prime functions that can possibly give you two different slopes. If the slopes are the same, then of course that will be differentiable. The function is differentiable. Is that all right? Any other questions for this tutorial? Sorry? 5 minutes break. Question 5. Okay, hold on. Yeah, this one. This one, what? Is it difficult to follow if, let's say, I sort x and y? Sorry, say that again? You cannot isolate x. You got x squared and ln x inside one equation, right? So the problem is, in the first place, that you cannot have x as a function of y explicitly. You can see this x squared and ln x. Not possible to extract out or factorize out the x when you have such different forms of the functions. So that's the motivation why we use implicit differentiation. If we can factorize out and isolate x as a function of y, then we just perform the usual differentiation can already. So implicit is useful, especially when you cannot factorize out that x. Is that okay? Yeah. Yeah. You mean this line? Sorry, which part? This part? Okay, you see, this part, when you differentiate respect to x, right? You are differentiating respect to x, correct now? So therefore, you have to use product rule here because it's x times another function of x. So therefore, I differentiate x, I put down y prime. Then this part, right, I differentiate y prime, I hold x. But when I differentiate y prime, I get y prime prime. Don't know. Okay, because you must understand that when you differentiate this y prime, you are differentiating y prime of x with respect to x. So there, hence, right, you are getting just y prime prime. You don't put a y prime beside again. You understand the thing here? Oh, at first you thought that I should add another y prime here. No, because y prime, let's say you have y prime of x. Now you differentiate y prime of x respect to x. But that's exactly y prime prime. So therefore, there's no more y prime term beside that y prime prime term already. Is that all right? Ken? Any other questions? Okay, I see also sad. I think I don't continue. Don't know why you all look very sad. Okay? So you have still quite a bit of time. You can ask me any doubts that you have, right, regarding the whatever parts of the lecture or tutorial. Okay? So you have no more questions. Then you just bear with me until tomorrow morning. I'll work out that thing. Or maybe later I work out. Okay? Then I'll upload the corrections. Okay? This part maybe I have a missing y term here. Yeah. So I'm just going to check it out. Sorry? Yeah, this one minus y. Then I got a plus 1 here. So chances are, probably I messed this up. Or maybe somewhere here I messed up. Okay, so let me just verify. Yeah, so that's all for today. Okay, thank you.